this energy conversion, electrochemical energy conversion and storage. So we have Professor Prakash Ghosh here who will be conducting the third session and continuing to its first session that was on the thermodynamics of fuel cell. Welcome, sir, and over to you.
Yeah, good afternoon, everybody. So I hope you had sufficient time for lunch. Just a minute, let me share my screen. Okay, so just before lunch we were discussing, and finally we came to a conclusion that we can get a voltage of, we'll be calling as an EMF. So let's say EMF is around 1 volt. Okay, and then second thing what we wanted to discuss when we were talking about the efficiency. So like Carnot efficiency, if you talk about, then this is given by delta G by delta H. And more specifically, if you do, then we'll be telling delta G naught by delta H naught, because you should maintain mention a particular temperature and pressure, otherwise it keeps on changing. And if you do this one, and if you try to put the value of delta G and delta H, and so this is 237 kilojoule per mole, and this is 286 kilojoule per mole, and this will be giving an efficiency of 83%. So this is this is not Carnot efficiency, what I was telling, fuel cell efficiency. So, but in case of Carnot efficiency, what you can see is this. If you go for Carnot efficiency, this one shows in the range. Let's take, we cannot tell because if you are not specifying a temperature, but let's take this is a 55% efficiency. So compared to this, you can see that this efficiency is much higher compared to the Carnot efficiency. But the problem what happens when you go for actual system, so let's actual fuel cell. So in that case, the efficiency will be in the range of 45 to 50%. That's what is being reported. So it is 45 to 50%. This is the actual efficiency what you are going to see now. And then if this has happened quite often, because also you should be knowing that there are also lobby on fuel cell who actually tries to promote fuel cell. There are other groups, they try to promote battery electric vehicles. Some other people, they try to promote IC engine based thing. So there are lots of things. So I was having a discussion somewhere where they were telling that if you tell that efficiency is 45%, 40% efficiency. So in that case, nowadays even good engine can go up to 35% efficiency, let's say. So you do not have any improvement or very marginal improvement. That's what they say. So in that case, even we should remember one thing when you are talking about the efficiency of fuel cell, 40 to 50%. Always we tell that this is minimum efficiency. This is minimum, because that's a problem that when you are rating, you always give an efficiency in the rated power. So efficiency as rated power, that's what we quote the efficiency, right? Rated power efficiency is 45 to 50% for fuel cell. Now let's say rated power efficiency for IC engine, internal combustion engine, is in the range, let's say 35%, very optimistic number we are taking. Okay. Now we should remember that rated power is only for rating a particular vehicle or particular system. But what happens when you are going in a partial power or partial load? That means if your power is less than your actual rated power. And where that particular thing, if you see that rated, if you go for IC engine based system and fuel cell based system. So in case of IC engine based system, if you have, let's say rated power is here, this is P rated, and efficiency is this one, let's say eta IC. So this is the efficiency if you take, and then if you go at partial load, then your efficiency comes down. This is the characteristics of IC engine, and that is going to happen because mostly all of us, we know that if you are driving a vehicle in a city, as you will not be able to maintain your velocity or speed at rated speed, so you will be always having the power consumption per kilometer will be always more. But in case of fuel cell, so that's what, if you tell a 55% efficiency, what you are telling Carnot efficiency, partial load, it will be coming down. If you talk about fuel cell and you have also rated power, P rated. Now, if this is the efficiency, again, you are telling, let's say 83%. Now, if you take the realistic number or something, and then what will happen? If you go, let's say this is our eta fuel cell here. Now, as you go at a higher partial power rate, your efficiency goes up. So, and this can go as high as 65% also. Yes, somebody, because Srivastava, you have something to ask? Okay, so all right. So now the catch is when you are referring a number, let's say 35%, this should be 35%. Okay, so if we are referring a number 35% for IC engine, let's say it IC engine and ETA fuel cell 40, let's say 45%, for example. Now there is a probability that it will be going up, this will go down. So if you take an average efficiency, it will be much lower than 35%. And if you take the average efficiency with fuel cell, it will be much higher than that, or higher than the 45%. So that's what, sometimes if you go for a drive, so average efficiency will be probably, minimum efficiency is 45%, but your average efficiency is going to be in the range of 55%, let's say. On the other hand, if you go for this IC engine based, it will be coming down.
முத்துவர்ணாச்சலம் சொல்லு பாப்பா, உங்களுக்கு என்ன டவுட்? கால்குலேஷன் சுதீஷ் ஓரளவு கொடுத்துட்டேப்பா. இன்னும் வரலையா? சரி, நான் அந்த சுதேஷை கான்டாக்ட் பண்றேன்.
Amit, can you mute him?
ஓகேப்பா, ஓகேப்பா.
That's what I'm trying, sir. I request all the participants to mute themselves. Otherwise, we are all teachers, and then it becomes, a little frustrating to get such interruptions. Please mute yourself if you are not using the mic, if you don't want to ask anything. Thank you.
Sir, you are muted, sir. Sir, please unmute yourself. Hello, sir.
Sir,
Yes,
please
yes.
unmute yourself, sir. We are not able to hear.
I unmuted myself now.
Thank
Thank you.
you. Thank you,
Thank
sir.
you. I do not know how much I have missed, but what I was trying to tell you that when we discuss about fuel cell and battery and the fuel cell and IC engine, because this is the thing, you see that at present we have a drivetrain based on all fossil fuel based, IC engine based. And people are talking that in by 2030, actually there is a huge drive now that by 2030 probably we'll be having fuel cell vehicle on road as well. But when we discuss, this is the important thing comes that this efficiency 35%, and we talk a lot about fuel cell, that if you are getting only 10% improvement in the efficiency, how does it matter? Is it really very big jump? So in that context, I was telling that 35% what we tell is that a maximum efficiency and it can come down, and 45% efficiency can go up, and average efficiency with a fuel cell car will be always in the range of 55 to 60% efficiency. But in the case of IC engine, probably 35%, but it will come down to probably 20 to 25%. And that depends where you are driving. So what I was telling that if you take the ETA theory, theoretical efficiency, I told that we can get from delta G by delta H. This all, as we are taking IC as a reference, so that's what always we are taking delta H as a denominator. So you can see that this gives us 237 by 286. This is kilojoule per mole. This is 83% what you get. But from that, if you go practically, as I am mentioning 43%, so there is a loss of 40% efficiency. So that means we are losing energy around 40%. So where this loss is happening? So this is what we are going to discuss in our electrochemistry, this particular now present lecture. So electrochemistry, I think sometimes you don't, I'll try to make it like a layman so that, because I know sometimes you will be having background of electrical or chemical or mechanical. So as it comes from variety of background, I'll try to make it like a layman, and that's what I'm not going my conventional slides where I teach in a different fashion. So we'll start with now electrochemistry part to understand that where is that loss is happening. So now we are planning for current voltage characteristic behavior of the fuel cell. And already you have discussed standard electrode potential which is E naught is equal to 1.23 volt. And we told that this is coming from thermodynamics. That means there is no electron transfer is happening solely from the, because for this whatever we have used delta G, and delta G is completely thermodynamic parameter and by NF, right? So this is, it does not talk about that how much current is flowing, because there will be lots of things happening. So now if we define here 1.23 volt, and this is voltage and this is current, and so what you can tell that this is corresponding to I is equal to 0. That means thermodynamically what you are going to get there, we have not talked about any electron transfer or anything related to the current. It is all related to the voltage. As we have not talked about current, so we can assume current is equal to 0. So now if I'm trying to plot on this graph, then at I is equal to 0, we can tell the voltage is equal to the thermodynamic potential. So that means at open circuit at I is equal to 0, what are the voltages you are getting? You can get E naught, you can get En or anything, let's say 1 volt or anything. That is all coming from thermodynamics. It's not coming from the kinetics. Now after that, what is kinetics? As I was telling you, you have water here. Now you want to take the water out of it. So what you have to do? You have to have this lid below this level. So because the potential energy here and potential energy here should be different. And then that's how you can pump the water from one tank to other tank. Similarly now, when you are making a fuel cell or any device, even battery also the same thing. Let's say, let us start with the battery. This is positive terminal, negative terminal, and you want to charge the battery. So if you want to charge the battery, you have to give a voltage higher than this side. You'll be giving higher voltage, so you can get current flowing from here to here. So that means you need to do an imbalance in the system. Imbalance in the system means it was at open circuit condition, it is an equilibrium condition. So at equilibrium condition, what happens? Let's say this is your junction, this side current and this side current is same. So that's what we call an equilibrium condition. Now if one side current decreases from this level to this level, let's say this is this level, and then you'll be getting a net current flowing through this. So now you can get a current flowing, let's say now in this case, you'll be having a net current flowing through this in this direction is this much, right? Because this black minus red, you are going to get the net current. Similarly, if you make that this side is becoming smaller like this, and then the other side remains bigger, so in that case, you'll be getting a current flowing from this side to this side. Like this. Okay, so so this is how it is going to happen. Now what we'll be doing, we have to do some imbalance, and if you are doing imbalance, so what you'll be doing, you will be coming down from this and then you'll be operating somewhere in different voltage which is less than your open circuit voltage. And if you do that, then you will start getting current. Like let's say if you have this water level, now if you make this water level, this, let's say this is tank, from here you are doing, this height difference will dictate actually the total how much water is going to flow, that m dot, right? So this actually is dictated by the energy difference, that's the potential energy difference between the 2 points. Similarly, in this case, when you are doing the same thing in voltage, so this is OCV, and then operating voltage, as much as you will be going less down, you'll be getting more and more current. So that means now this is what you are seeing here at open circuit condition. After that, you have come to a point, let's say this point, where the voltage is, let's say this point, and voltage is this much, and then you'll be getting a current coming like this, let's say. If you have, let's say this point, you'll be getting a current coming like this. So this is how, as you will be increasing your current, or your current will be increased if your operating potential comes down. And this is the characteristic curve what you can get. And you can see, let's say now I'm going to put like this, some behavior. What is now if I try to plot power on this axis, and what you can see that at this point the power is 0, at this point is power is 0. Why? At this point your current is 0, so power is equal to, what is power is equal to V into I. At this point your current is there but voltage is 0, so your power is also 0. But in between you'll be getting something like this. Even then you will be getting a maximum point, and this could be also your rated power, rated current, let's say I rated, and corresponding to that you'll be getting a rated power. Now, so this is what I was telling, that as now if you are going from this side to this side, so you are supposed to get, if I try to draw once again the same graph here, then I'm not taking anything now. Behavior I'm taking now linear. After that we'll start discussing that the how the behavior is going to be. So next one, what you can see is you expect 1.23 volt, but you are getting here, let's say 0.6 volt. So power, now what you can see here, if I draw a graph like this, then I'll be getting one graph like this. Other area I'll be getting like this. What is that? This is voltage. Here, this is voltage multiplied by the current. This is current, right? This side is current, I, ampere, let's say. And this is voltage. Now, if I multiply this by this, I'm going to get the power. But which power is this? This is the electrical power. But ideally, how much I should have got? Ideally, I should have got this much area, right? But because of the loss, we have lost this much of area. That's the total energy. What you can see is this much. Sorry, this is the total amount of energy. Out of that, this much is your electrical power from fuel cell, and this much is your efficiency loss, but it's not a loss. Actually, this is your thermal energy what you are going to get. So anytime if you are going from right hand side to left hand side, this area is coming down. Blue area is decreasing and red area is increasing. That's the reason what will be happening. You will be also getting loss will be reduced. OK, your power is increasing at the same time because loss is also decreasing, right? So one you will be getting higher power as well as also you'll be getting higher loss is also minimum. Sorry, don't take it will not be increasing power. I'm sorry, extremely sorry. Your power will be coming down definitely because that will depend on the area of this graph. But what is going to happen? The loss, this area is always coming down, this area. So this green area, the blue area is coming down, and as blue area is your thermal energy and we call it as a loss. So your energy loss will be coming down, so efficiency is going to increase. Now, in previous lecture earlier, not mine, Amit was discussing in CHP mode. So what happened in CHP mode, you try to use electrical energy as well as you try to use the heat. And that's what even we also try to do in some of the applications. We find it's going to be very useful because our fuel cell operates at the room temperature around 80 to 180 degrees centigrade, let's say, a particular fuel cell. And then now what happened if you have the fuel cell and you are giving an energy, let's say E, out of that you are getting 0.5 E electrical and 0.5 E thermal. I hope you understand that one because the total energy is, and I'm assuming 50% efficiency for simplicity. So this is electrical and 0.5 E thermal. So this I can use for my electrical purpose, and E thermal what I'm getting is also, so if I have a 1 kilowatt system, so then I'll be getting 1 kilowatt thermal energy also, right? It's an E thermal, right? Thermal. Now this 1 kilowatt thermal, and at which temperature I'm going to get in the range of 80 degrees centigrade. If I don't remove this heat, and if like a fuel cell like this, and this heat is being added up all the time, then what will happen? Your temperature you will not be also able to maintain. So this 80 degrees centigrade will not be maintained, it will be going up. So if you want to maintain the operating temperature, you have to recover the heat of 0.5 E thermal. And if you recover the heat, so you can see now the total energy, how much you are giving as a fuel, 50% of that, or 1 minus eta fuel cell, is that you are going to get as an heat, right? And this is at 80 degrees centigrade. And there are lots of applications, at least for taking bath in geyser, we can use this heat and then we can do lots of applications. In lots of the places where you need space heating, in that case, you can easily use this particular heat and then keep and make a space heating. And if you do that, then your efficiency will be actually much higher, and that is known as CHP mode. So now we have understood that this graph, what we are seeing, and if I tell this is my operating point, so then this is, let's say, this percent, if this is total 1, so this percent is my electrical efficiency, and this is thermal efficiency, or you can, or in that sense, so thermal energy. Mostly that's what you can assume. So now, if we have understood this one, that we need to operate, we cannot operate at open circuit condition, because if we are operating at open circuit condition, we will not be getting the flow of electron. If we don't get flow of electron, we will not be able to get current. And if we don't get a current, our purpose will be defeated, because we want to use, ultimately, we want to produce power out of it. So now we want to discuss the kinetics behavior. This graph what I'm showing, how does it look like? Does it look like this, or it looks like this, or it looks like this? So this could be different thing, right? So this is always I'm forgetting to write. This is current and this is voltage always. In this case, in case of fuel cell, always the voltage is the dependent and current is the independent axis. Okay, on the independent axis. So now, which is the form is going to take? Whether it's going to take like this, whether it's going to take like this, whether it's going to take like this, or combination or all. That's what we are going to discuss. The first one, when you are talking about this loss, we call it a kinetic loss. What is kinetic loss? Let's say when electron is moving, because earlier it was not, there's no net current flowing from one side to other side. Now as electron starts moving, then we'll be having, I'm not going in more detail, because let's say this is a fuel cell, this side you will be having one reaction on the anode side, and cathode side will be having another reaction, and that's what we talk about the kinetics. So this is one side reaction, this is the other side reaction, what is going to happen, and then kinetics will be playing a role. Now in this kinetics there are three important terminology we call it. One is that activation, we call it activation over potential. Sometimes we call it activation polarization. Ultimately, what is this? This because you know that because of this, you want to draw some current, it will be deviating from its open circuit condition to some value, and now where it will be going, that depends on the characteristics of your system. But this particular thing we will be calling as, because deviating from its open circuit condition is known as polarization, and this polarization could be positive, it could be negative based on your system. And in case of fuel cell, polarization is negative in that sense that it will come down, so your voltage will come down, and sometimes afterwards also will be. So if you have a battery, let's say I'm taking a battery, you have a 2-volt battery, so it's a 2-volt battery. Now when you are charging, then your operating voltage from where you are giving, it should be greater than 2 volt, sorry, greater than 2 volt E applied. When you are discharging, then it should be less than 2 volt. That's what, this is your open circuit voltage, 2 volt. Will be giving more than 2 volt, you are giving less than 2 volt. Or does mean, let's say for at a particular time, you are charging your battery at voltage of 2.2 volt. That means if you take the over potential or polarization, that means how much is this? This much. The deviation from your standard condition to your or open circuit condition to this is your eta over potential we call. So, and how much is this? This difference, this is 2 volt. Let's say I'm talking about charging. So this is 2.2 volt. So this is 0.2 volt. 0.2 volt. So that means I have given now a jump of 0.2 volt so that I can push now electron to move in one direction. So let's say now it is moving in this direction. Now if I do similarly, let's say 1.8 volt, now again I have given 0.2 but in opposite direction, so current will be now flowing in opposite direction, right? That's how it works. And that's what happened in case of battery. When you are charging, you will be giving more than your battery open circuit voltage, and when you are discharging, you will be giving less than that voltage, and that's what it works. And that is called polarization. Now this polarization, so what you have seen, let's say when I was telling you earlier here, so this is the polarization. This is polarization, right? And because of the polarization, you will be getting the thermal energy mostly. There will be some other things, but now for time being, as a preliminary lecture, let us assume this is the polarization. So this is also a polarization, but this polarization could be due to different reason, and that's what we are going to discuss. So that loss what you are going to get, as I told, one is because of the activation loss over potential. Second one, if there is any electrical system, you'll be also having a ohmic loss. So you'll be having an ohmic drop, because all the systems they'll be having so by ohmic polarization. And third one, what we call it is the concentration polarization. So these are the three major things that what comes, and then because what we'll be seeing, that loss what you are seeing is an important or contribution of all these three at a particular point. Okay, so now we'll start understanding what is activation over potential. In case of activation over potential, let's say if you take this current and voltage, you are here. Now you do not have any net current. Let's say you are at a static point now at particular time in a car. Now you want to move. So you'll be having a friction called static friction, and you'll be having a loss. But as soon as it starts moving, then you'll not be having any more static friction, then you'll be having a different friction, right? So similarly, when you are initiating, because at this point your current is zero, that means there is no movement of electron as such. Net movement is better to say net movement. So as there is no net movement and current is zero, now when you are trying to initiate this process, that means you are trying to initiate the reaction, you will be getting a loss. Like a car, you are initiating and then you will be having some loss. And this particular loss is known as activation loss. So just you are trying to activate your system. So what you expect now, as you know that your frictional loss will be almost prominent when you are at the initial phase. Then after that, as you are accelerating, then after that that particular loss will be coming down only for acceleration, because you will be changing in momentum, you will be also having some loss. So in the beginning of your speed, now if you corollary, if you see speed, so in the beginning you will be having, after that it will be almost steady. So if I take a velocity versus power, so initially you have higher, and then after that it will be coming down like this, right? You don't need that much of, because loss comes down. So, and this is how you can. So similarly, if I try to talk about activation over potential, it looks like this. This is the behavior of eta. Now earlier I was telling eta efficiency, now I am telling eta as an over potential loss. This is the terminology that is being used. So this is eta activation, and it looks like this. This is the behavior. And so if I try to show the characteristic curve now, so I expected like this, E naught. Now what I expect a loss of this much. So how this graph should look like now? Isn't it? It will be looking like this. Like this. Yes. So this is now the characteristic curve where I'm trying to show you is that E naught minus eta activation. Right? I have only considered activation loss. Second one, so this is one. So again, I am missing out sometimes current, and this is voltage. So what we have shown that you'll be having some loss looking like this. Because of that, you'll be getting a trend coming like this, and this is the performance of the characteristic curve of a fuel cell if you consider only activation. But sometimes back we are also telling that there is also ohmic loss, because internally there will be some resistance from the membrane, from the electrode, and I think when Amit is discussing that one system level, probably he'll be telling. So you'll be having different types of losses, ohmic losses. So ohmic losses is coming because of the ohmic resistance coming or internal resistance coming from the different components inside the cell. Like membrane will be having component resistance, electrode will be having resistance. Sometimes there will be contact problems, so contact resistance. So all this resistance is giving an R resistance, let's say. You can call it an internal resistance. Again, I try to plot current versus voltage, and then how this loss, ohmic loss, looks like. As we know, V is equal to IR, so it will be linear. And this slope is actually given by the resistance. And if I try to plot now the same thing, I expected 1.23 E naught, but because of this, now this curve will be looking like this. This is a modified graph. So what is this? This is E naught. What is this graph? E naught minus eta ohmic. Right? So this is the ohmic drop. So only if we consider ohmic loss, then it will be looking like that. So if you combine now these two, 1 plus 2, and how it is going to look like now? This is current, voltage. This is my E naught. And what I've seen in the beginning, I'll be having a graph like this. This is coming from activation over potential. After that, it was going like this. Like this, right? This is only activation. With ohmic, it was going like this. Like this, linear. If I combine these two, then I'll be getting a graph which is looking like this, right? So you have a region where actually comes down very fast. Then after that, and this is because of the activation zone. And after that, when activation zone is not prominent here, that time ohmic zone start dominating, right? This is the ohmic zone. All right. So this is the characteristic curve. If I assume that when I am considering only ohmic activation and ohmic, and these two things you cannot avoid. So this is the characteristic curve you will be getting for fuel cell. Because you cannot avoid activation like a car. If you want to initiate your car, you cannot avoid the startup. And you cannot also avoid the internal resistance of your system, because no way you can make a system which is not having any internal resistance. So ideally you will be getting this type of characteristic curve. But there is the third terminology what I was talking about, is that the concentration. So concentration over potential. For that, we need to understand exactly what happens in a fuel cell system. So let us try to understand this. This is my electrode. This is my membrane. This is other side electrode. And membrane is not permeable to the gas. And this is my electrode. I'm just trying to make different thing. And then this is my gasket, sorry, is the flow field through which my gas is going to go now, like this. Let's say I'm giving hydrogen is coming. Now what happens if I try to see this? This is hydrogen is coming and going. Now reaction happens here. Here you need a gas. How it is going to happen? If I magnify here, so what is happening? Here hydrogen is coming this way. Your reaction is happening. So this is your stream of hydrogen going like this. You are given a pressure P. So let's say you have also a pressure, inlet pressure P in. And then after that, you have a electrode here in that electrode, and then you have your membrane. Now this electrode is porous, sorry. This electrode is porous. So that means through it, gas can go very easily. And reaction is happening for a time being. Let us assume reaction is happening here. So that means this is the place we can tell as your hydrogen sink for that side. Why hydrogen sink? Because here reaction is happening and H2 is getting consumed and becoming H plus ion plus electron. So H2 is getting consumed here and here you are supplying H2, right? So that means now you expect that gas should flow like this. And this flow happens because of the pressure difference. So if you have also pressure here same as pressure inlet, do you think that gas will be flowing from this side to this side? There is no driving force. Gas will be only flowing through this if it is passing from this side to this side, only that if your P site, reaction site is less than P input. Then only you will be, and this is because of the diffusion. So here the flow of the gases through the electrode is because of diffusion, and this diffusion will be only happening if you have a pressure. Now you can see that how much current it is going to go here from here till here, that depends on delta P. You assume a pipe, and if I ask you that how much water will be flowing through this, it depends on what. Definitely m dot is directly proportional to delta P. If you give more pressure drop across this particular pipe, and if you keep pipe length constant, more and more water is going. So now what happened? If you are giving more and more pressure drop, then how will you be getting that more and more pressure drop? So you have to, if you want to create delta P more and more, so your reaction side pressure. Now I am going to create delta P. What is delta P? Is P inlet minus P reaction site. If I want to draw more current, if I want to increase current, what I have to give? I have to give more hydrogen, because hydrogen is getting, let's say if 1 mole of hydrogen is going to give me 2 mole of electron. So if I supply more and more hydrogen, m dot H is more and more, you will be getting more and more electron per unit time. So your current will be increasing. What is current? Current is the electron per unit time. So that means if you are increasing current, that means you are extracting more and more electron, or electron you are extracting at higher rate. And if you are extracting electron, that means where from electron is coming? From hydrogen electron is coming, right? So you are getting more and more electron, means your hydrogen is also getting consumed, and where it is getting consumed here. Now to get more hydrogen, what you have to do? You have to increase the flow rate, but your inlet is fixed because that is your input pressure. As your inlet pressure is fixed, and if you want to increase the delta P so that your I is also increased, in that case your P reaction site has to come down, then only you will be able to do. So because this is fixed here, you cannot change. So if you reduce this one, then only you will be able to get this. Now if you reduce this pressure, you go back to your thermodynamics. You can see that we are discussing your E naught, not E naught, E N also is a function of your pressure and temperature. Now your reaction site pressure has come down. If reaction site pressure comes down, your performance of course will be coming down, right? So then we come to the third point, is that concentration over potential is given by a loss, because if you are drawing very small current I, then your concentration delta P is not that much significant. So your concentration is not that significant. But if you draw more and more current, then you'll be having a problem, and then like this, and then you'll be getting like this. And this particular thing we call IL is the limiting current, because you cannot go beyond this, because at this point of time, what will happen? Your pressure, reaction side pressure, P at reaction site will be equal to 0. And that time, what is the maximum delta P? Delta P is equal to your P inlet, right? That's the maximum. You cannot get more than this delta P. And because of this delta P, you will be getting a maximum m dot H2. And this maximum m dot H2 will be also related to your maximum n electron. And after this, and this is as per unit time m dot, so that restricts your current, and that is known as limiting current. So if you are operating at a particular pressure, your fuel cell, then the flow to the site, the flow of the gas to the reaction site will be coming down, and then if you increase the delta P, flow rate will be increasing and your current will be increasing, but after a certain limit you cannot increase further flow rate because you cannot increase the pressure difference, because pressure difference can be maximum equal to your inlet pressure, and that is the situation your reaction site pressure is 0. And under that situation, what is going to happen? If it is your E naught, then you'll be getting the characteristic curve looking like this, very little, and then all of a sudden comes down to 0. So at limiting current, your your voltage of a cell will be 0. Why? Because your reaction site, P reaction site is 0. As your P reaction site, so there is no gas is left there. So that's why your P reaction site is 0. So that's why your voltage will be coming down. So you will be getting this situation. So now what we have seen till this now, earlier I was telling that we have a system where if you combine only one activation over potential, then this is your theoretical condition, then it will be looking like this. Sorry. Like this. This is only E naught minus eta activation. This is I, this is voltage, 1.23 volt. But as soon as I also introduce the ohmic drop, then it looks like this. And this is E naught minus eta activation minus eta ohmic. Now third one, if I try to introduce, now what I was talking about the concentration, also there, so then it will be looking, because concentration has nothing to do in this region. It only happens, let's say this is my IL, sorry, the limiting current. So it will be happening in this region only. So here almost 0, and so that's why nothing is going to change here in this graph that much, and slowly you'll be getting, and then it starts dominating like this. So this is what we have got, is a combination of activation over potential or activation loss, then ohmic loss, and this one is also, so this is eta E naught minus, so this is E is equal to, so E is equal to, this is E is equal to E naught minus eta activation, eta ohmic, eta concentration. This is all. Okay, so I'm stopping here, and I'll be taking a set of questions, because this is what I wanted to discuss, because there are lots of things which I can discuss further, but I'll be only discussing that if I get a confidence, yes, you have got it, because after this I can enter in the reaction kinetics and different types of activation losses equation, ohmic losses equation, mass concentration losses equations. But because this was like a layman discussion, I will be happy if I don't get any question, then probably I'll be feeling that I should not pour on you more than this information. So I think Amit, you can just open the floor for discussion.
Hello.
Thank you, sir. Thank you so very much for the talk. So any questions from the participants?
Good afternoon, sir. This is Deshakira calling from Rajiv Gandhi University of Knowledge Technology, sir, Kadapa. Sir, I would like to request you to please suggest some books regarding the morning lecture and the current lecture, sir. Any basic fundamental books that we can follow for that?
There are books. Unfortunately, fuel cell books are very expensive. I have written. I was in the middle of writing a book. Amit knows very well. This is a. I do not know. It's an how many years plan. Okay. So what I'll do, I'll give Amit a. I think Amit already you have, right, my dog, that book. Some chapters are.
Yes, sir. I have one or two chapters with me. Hello?
Yes.
Yes, sir.
Yeah, I have two chapters with me.
No, what I'll do, I have a complete one. So I'll be giving both the chapters, thermodynamics and uh, uh, this one, electrochemistry, both the chapters, whatever I have written, I'll be giving that thing. But
Yeah,
you have to read it very carefully.
that's what, sir. Because the morning lecture was extraordinary and I couldn't find that sort of explanation in any of the books till now. So for that, I was asking about any fundamental books regarding this morning lecture as well as now lecture.
Yeah, so I'll just share with you. Okay, so but other is there is a good book. I think Orion, right? What is his name? But this is all.
Rian Are, sir.
Rian Array, yeah. But these are all very expensive books, and I do not like that for our Indian reader. I wanted to have a very means cost-effective version of a book. So that's the reason I started writing. So
Yes,
I'll
sir.
share with you that particular. It's a very raw file where there will be lots of language mistakes. There will be lots of reference problem.
Yes,
Probably those things you have to bear, and then other is the main equations and other things are almost there.
yes. Means I have gone through this book is ready as well as this Gordon Parker book, but I couldn't get the clarity in those books. For that, I am asking. Thank you so much again.
No, I think I'm not sure because probably I was trying to give you, because in this lecture you'll be finding I was trying to use as minimum as possible, that I was using equations and these things. At least
Yes, sir.
theoretically, if we understand and if we can visualize even this, what is
Yeah.
happening, then we can get the now why this shape is linear, that you can understand Ohm's law is linear, but
Yeah.
why other portion is that one, other portion, there's thing, then we can go in the equations or other thing. But
Yeah.
I think if you have got this idea that yes, fuel cell, why the efficiency and why it is coming down and what are the different things which we
Yes.
can avoid, which we cannot avoid.
Yes, sir.
Always now in this characteristic curve, what you have seen, we cannot avoid activation loss, we
Yes,
cannot
sir.
avoid ohmic loss, but we can avoid concentration loss.
Yes.
And but what we can do in case of activation loss and in case of ohmic loss, we can mitigate the problem and can reduce it, but we cannot make it zero.
Okay, sir.
And so what happened that next one, that activation loss, what we are talking about, there all the catalyst comes into picture. Now whether platinum
Yes.
or iron, which one will be taking. So their activation losses comes, and I'll start discussing that one. But before that, I wanted to have few more questions, then I can go ahead with that. Maybe I have another probably 20 minutes I can discuss in that if I get a good question here. Otherwise, if you have one or two people, then probably I can have a personal interaction or I can share with you information, because I don't want to load people with, because sometimes I'm trying to tell in even our normal lecture, we take probably 3 to 4 weeks time to take the same thing. So I don't want to overload you people.
Okay, sir. Thank you.
Welcome. Any other
Yes,
question?
yes, sir. This is Dr. Sudha from Bangalore Institute of Technology, Bangalore. So far, we are discussing only about the voltage and the factors affecting the voltage. How about current, sir? Are we going to see it in the next session, or this is the end of it?
I think after lunch I was talking about current only. If you see the characteristic curve,
VI characteristics you're talking.
the I is the current, right? I'm telling that if you talk about a different current, so then we are talking about the current only now.
No, no, sir. If we want to increase the current capability of a particular cell, fuel
Huh.
cell,
Huh.
so how that can be done?
So that let's say I was giving an example. If you want to draw, let's say there is a two buckets, okay, and you are connecting with a pipe. Then if you want to draw in a higher speed or higher rate from one bucket to other bucket, what you do? You try to generate an higher height difference, right? If you change the difference or if you increase the height difference, the total potential energy difference will be more. You will be having higher flow rate, right? This is what we know in general. In this case, what I was telling that if you want to draw more and more current, you will try to create an over potential eta higher. That means open circuit condition, what I was telling 1.23 volt. Now at which voltage you are going to operate, because if you operate at 1.0. Now as you keep on decreasing your operating voltage from 1.23 volt, that's what I was showing in this characteristic curve. You are going on the right hand side.
Yes, sir.
Then you are actually, your voltage is coming down, right?
Yes.
So that voltage, now that voltage is nothing but a potential energy of the water level. So if you take two different water level, as you level in one bucket, you are taking down and down and down, you'll be getting more and more pressure drop, and you'll be getting faster rate water supply, flow. Similarly, in this case, as you are going down from your open circuit voltage as low as possible, then you will be getting more and more electron flow, and more electron flow rate is your current. Right? And how much is this that you can get infinite current? No. In case of, let's say, if you have normal electrical connection grid, and if you short circuit, you get infinite current. That's what we talk about. But in our case, we'll not be getting an infinite current. We'll be getting a finite current, is the limiting current, IL, what I was trying to show. Why? Because when you are taking an, let's say, grid you can think as an infinite source of electron. So if you short circuit it, you can get infinite current per unit time. So you can get infinite electron per unit time. So you can get infinite current. That's what we think in case of other sources like normal grid. But in our case, our electron depends on what? Can you tell me this one, that how many electrons I'm going to get will depend on what?
It depends on concentration.
It depends on hydrogen consumption.
Hydrogen consumption.
Right? So if I use 1 mole of hydrogen consumption, I am restricted to 2 mole of electron. I will not be getting more than that.
Yeah.
Now hydrogen, if I want to get 1 mole of hydrogen, where I was showing a place that the reaction site, let me go again so I can, when I'm discussing, let me use my board again so it becomes easier. Okay, so what I was telling here earlier, that this is my limiting current, IL.
We are not able to see the board, sir.
You are not able to see the board?
No.
No, sir. It's visible. I think it's just the delay that's playing.
Yeah. Okay. Yes. Yes, sir.
Yeah.
Now it is visible.
Yeah. Because I wanted to share with you, I am also having my one screen like you, and I see my own screen as well. And I see, but I ask you people as a courtesy, but I see always I can see my writing. So I was surprised when you told that you cannot see. Then I thought, is that some magic is happening at my end?
No, sir. Probably the delay is.
Delay. Yeah. Okay. So what you are seeing, this is the limiting current. And I told, now if you see physically what happens, this is my electrode. Here I am passing the gas like this. Earlier I was showing, right? This is inlet, this is outlet. What Amit has shown earlier, and this is my stream is coming, and this is we will be calling as a flow field. I think he has told or he will be telling. And this is my electrode, which is a porous electrode. Through this it is going, and this is because of the delta P I am creating. And what is this delta P? Delta P is equal to P inlet minus P at this point, P reaction site, RS, PRS. So now this, earlier I was telling I want to get 2 mole of electron. I need 1 mole of hydrogen at this site. Now for that, who is going to give me this hydrogen? This stream, right? Because this is moving, so they are giving me. So now I have to create a delta P so that I can get this much of hydrogen. 1 mole of hydrogen is coming through this. So what happened? What is the maximum delta P I can get across this? This is the difference, right? When delta P is equal to 0 when my this pressure and this pressure is equal. That means I am not consuming anything here, no consumption here. Then P raise is equal to P input, right? So both of them are equal. So no flow is happening here and here, right? Now, what will be the maximum when this PRS becomes equal to 0? Then what will be delta P? That time delta P is equal to P in, right? So that is the maximum pressure I can give. And for this maximum pressure, I am also limited to a maximum hydrogen flow from here till here. I cannot go more than that. And if I can get that much, I am also restricted to n. If it's a n number of hydrogen is moving, so I am restricted to 2n electron per unit time. So this is, and this corresponds to my limiting current. So I cannot go beyond that. And this is what I was telling, that if you have an open circuit voltage here, and if it is coming down, so then I am, as it is coming down more and more, this is the voltage coming down. This is my operating points. So I am getting now more and more current, right? So voltage here current is more like that is I1, I2, I3, right? So, and then finally, now this behavior is not linear. This behavior is initially it is coming like this, then it is linear, then I'm like this. So this portion is, we call it because of activation dominated, because when your reaction is, this is what I told, I is equal to 0, then your current starts increasing. So that's the time I told, like your car you are activating and starting now for your journey. So that's what I was telling you also, U is equal to 0 here. So this time the loss will be telling us activation dominated. Then after that it will be ohmic dominated, because in this portion your I is very less, right? I is tends to 0, let's say. And if I tends to 0, what is ohmic loss? I into R. So
very less.
Very less. So that's why we'll be telling in this region ohmic is not dominating, it is contributing. Always I have written the total loss eta is equal to eta activation plus eta ohmic plus eta concentration. Now eta activation is dominating here and ohmic is not dominating. If you remember the 3 graphs, if I try to draw now losses graph, this is the activation loss. This is ohmic loss. This is concentration loss. So in this region, if you see, it is, and if you see the slope, so this is the highest slope, this is the lowest slope, and this is moderate, and this slope is the resistance. So in this region, what we'll be finding from the slope, that because slope is that ultimately resistance what we talk about, right? So in this case, in this region, it is activation dominated. After this, if you go here, you'll be seeing that this is coming, it is slope is becoming horizontal, but this slope is still in this. So in this region, we'll be telling that it is ohmic zone. But ohmic zone doesn't mean that other one is 0, other one is minimum. And then third one, after this point, you can see that starts increasing now slope because of concentration plot. So that's what the third area will be telling us. That so this is our activation, this is our ohmic, this is our concentration dominated. So, and if you combine these 3 losses, combining these I was showing together now individually, combining this is activation loss, ohmic loss, concentration loss, and this is the behavior of the loss with respect to current, and this is voltage. Okay, now loss means I have to subtract that from what? I'll be subtracting it from my E open circuit potential. Okay, sometimes we can tell also VOC. Okay, so this, so if we subtract from VOC, and then now new equation, if we write VOC, V is equal to VOC minus my eta loss. Okay, this is this one. So these characteristics will be looking now like this. This was fixed. Say here my, what is the eta loss? 0. So this is my initial point. Now it will be exactly following this trend, but in opposite. So now it is like this. And so this is the, so this is, what is this? This is current, this voltage. So at any current, what is the voltage you'll be getting? Okay.
Okay, sir. Thank you, sir.
But
Sir, is
I'm
it possible
sorry,
that we can get a small PowerPoint presentation on what you spoke today, sir?
No,
PPT.
I'll be giving you a write-up of. I'll be giving you a write-up of all these things separately. Okay, that I think Amit will be distributing. It's a
Okay,
Word document. Okay.
Okay, thank you.
Excuse me, sir.
Yeah, please.
Sir, I'm Dr. Madhu Sharma from UPS Dehradun. Now my understanding is little more good after explaining, understanding what you have explained. So in most of the reason, the relation between voltage and current is linear.
It is in this region. It is not linear.
In a particular region, it is the linear.
Yes.
Otherwise, initial close to origin, it is non-linear.
Yes.
This is my understanding. Yes, sir. What happened when it is connected to the load?
Okay.
It means
No.
with this we are discussing about the internal resistance of the cell.
Okay. Okay. All right.
So means for this particular device, we can say this is a voltage source or this is a current source.
Okay.
So what to say means I'm confused. It is
Okay.
more close to voltage source or it is more close to current source, because we are also concentration talking about the concentration.
It looks like you are an electrical engineer.
Yes, sir.
Okay, I'm not. Okay, would you kindly define little bit of electric? What is that? Current source and voltage source? Then I'll be only explaining it. Okay.
Actually, sir, means in the voltage source we have a minimum resistance.
Okay.
And in a current source, we have in parallel the infinite resistance. And in voltage source, we have in series the means as minimum as or zero resistance.
I got it. I was trying to tell in different way. I was trying to tell that physically, if I tell a current source,
okay.
So what does it mean physically? You will not be, because let's say a source is current or voltage. How will you be defining that? Okay, so current source means, what I understand is that your voltage, you can give infinite current and your voltage will not be polarized.
Okay. Because means that solar cell also is more that the current source.
Yeah, because in case of solar cell, the total current, short circuit current, what you are going to get depends on the illumination of light.
Yes.
So if you, that's what how much currents you are going to get is restricted by your current. Okay.
Yes.
So similarly, in this case, if you want to tell, then we can tell is a current source, because in this case, the current is determined because you cannot get infinite current.
Yeah.
Okay. And as you are not, in case of solar cell also, you will not be getting an infinite current. You will be getting maximum short circuit current. Why? Because your short circuit current is limited by what? Short circuit current is limited by your, I'm sorry, other people, as he has mentioned solar cell, so I'm taking that reference. And if I teach, actually I teach solar cell and fuel cell basics almost in the same fashion, because even equation and everything I can show that, okay, it works at the same fashion. Because in case of solar cell, you have p-n junction. In case of fuel cell, you have electrode and electrolyte interface. This is another junction. Okay, so just to answer your question, in case of solar cell, you know that the short circuit current comes from the generation and that generation carrier. And that generation carrier, there are two different types of generation carrier. One is that we call it a thermally generated carrier. Also, we know they are known as minority carrier. And
yes.
Other one is that photo-generated carrier, and photo-generated carrier is what we talk about the short circuit current which is coming from. And this photo-generated carrier is restricted by the intensity of light, because one photon gives you one electron hole pair, that electron. Now the intensity of light is dependent on the number of photons per unit area. Per unit time.
I know, sir, but for solar cell, we do have a standard equation that is non-linear and biquadratic, the relation between the voltage and the current. So for the fuel cell, we do have the standard equations. That relates
yeah.
voltage and current.
Yes, yes. So whatever I have drawn now, I was trying to make it as a layman type. Now I can put all of them this equation. How, like, I already have written the equation like VOCV minus eta loss, right? Now eta
Yeah.
loss, eta activation. I can also write the equation. Already I'll be sharing with you people the equation, because equation you can read yourself. So I have, like, in case of solar cell, you get this graph, right? This is your
Yeah.
I naught e to the power QV by KT minus 1.
Yeah,
This
yeah.
is
I got
direct
it.
current, right? And
Yeah.
and from there you subtract your IL, and then you do the IL minus IT, and you'll be getting your current. That's yours.
Yeah.
That's not the relation, right? Here, what we
Yeah.
are trying to do the same thing. Voltage is equal to E naught, and E naught is coming from your delta G by NF minus eta loss. Now this eta loss I'm not writing now, because eta activation is a little bit complicated. Eta ohmic is very easy, because eta ohmic you can write simply I into R, right? Internal resistance.
Yeah. Yeah.
Okay. So, but no, to come to your question, that as we are telling, like, you can see this portion, like it's a short circuit current in case of solar cell, it is limited. You cannot get infinite current. If you have a voltage source, if you short circuit it, are you going to get finite current or infinite current?
Of course, limited.
No, in case of voltage source.
No, that is then depending upon the load.
If you do short circuit.
And infinite current, so we cannot get. No?
In case of short circuiting.
In case of, there is a limit of short circuit current. No?
If you short circuit and voltage, ideal voltage source.
Yeah.
Then what will be the current? This will be actually, you can check also parallel and series. Okay, if you put a short circuit means you will be having 0 total. So
yes.
now you are in parallel. You are parallel in 0. Okay, so your current will be infinite.
Yeah, infinite.
Yes. So, but in case of this solar cell and fuel cell, as you are not getting your infinite current at voltage is equal to 0, because that's the short circuiting.
Yeah.
Fine. So this is a current source in that sense, if you talk about, right? That's what I wanted to just tell you. And then why it is that? Because this particular current is limited by your hydrogen flow. So next thing I wanted to just, you had a different question, just we got diverted from there to this one. Or would you kindly again repeat the question, so I'll catch that answer.
Sorry, I'm diverted. Now I am how to relate this voltage and current when connected to the load.
Connected to, that's a question. Yeah, connected. So now let's say you have a battery here.
Okay.
And it is at open circuit voltage 1.2 volt. So that is mine open circuit voltage. I'm telling you that you are operating at 1 volt. How will you be doing this?
Because of internal resistance.
No. If your current is not flowing, your voltage will never come. So at open circuit voltage, no current flows.
Yeah, of course, no current flows.
So if no current flows, then how you get IR loss? I is 0.
I is 0. Yeah.
So IR is also 0. So your VOCV and VE operating is same. So at open circuit condition, your open circuit voltage and your let's say theoretical voltage, or it's a junction. It's actually we are messing it up because we are telling internal resistance this one. So this is an internal resistance. This is we call terminal voltage. This is we call theoretical voltage here at the junction. So what I'm trying to tell that this will be only happening the same thing. You try to make some arrangement and so that your potential comes down here. So what do you make that arrangement? You connected load only. And if this load is connected such that what is initial load RL tends to infinity. That's open circuit condition.
Open circuit. Yeah.
Then slowly you start decreasing this load. As you start decreasing the load, automatically this voltage will start coming down.
Yes.
So when you are telling 1 volt operating, how do you operate? Actually, you connect your power, your load, and you control the power. So when I'm telling this particular characteristic curve, I'll again draw the graph. So let's say this is my graph, characteristic graph. And if I draw the power curve like this only, sorry, like this. Okay. Now if you take different points, you'll be getting corresponding to this different power point. This is the power. Let's say this is my power graph, and this is my power graph. Okay, so this is my power curve for this point. For this point, this is my power curve. So what is happening at these different points as my open circuit voltage, I am operating voltage is changing. How? Because I have connected, this is my fuel cell. It is being connected to a load, and this is, let's say, a variable load. So when I make it infinite, it goes to open circuit voltage. Now you keep on changing your resistance and then reducing resistance, and this will start moving in this direction. Okay, so that means when I'm telling all these points, I am actually talking about different load points. This corresponds to a load of this much power. This corresponds to a load of this much power. This corresponds to load of this much power. And this is maximum. After that, again, it starts coming down. So your question was that how do you connect the power or something? So it is actually characteristic curves itself talks about the power and the load. And all this, if you are not connecting any power, then you are at this point.
Yes.
And as you are increasing your power from this is this much power, this is this much power, probably this is this much power, and this is, let's say, this much power. So as you are going from left hand side to right hand side, your power is increasing up to this point. After that, again, your power will start coming down. This is because of, you know, that if you integrate Vi, if you differentiate Vi with respect to I or V anything, then you'll be getting that, you'll be getting maximum power for when your this R is equal to your internal. So this is that's what we know, that maximum power point, that when your external load resistance is equal to your internal resistance. And after that point, it will start coming down. I hope I could answer your question.
Yeah, thank you so much, sir.
Yeah, okay, thanks for your question. Thanks. Okay. Anybody else?
Sir, hello, sir.
Yes, please go ahead.
Yeah, so I'm Biju. I'm faculty in mechanical engineering at Government Engineering College, Calicut. So my question is like, I could see that in most of the fuel cell cases, the utilization factor, fuel utilization is always kept low, say 80 to 90 something. So I guess it is because of this, to avoid this concentration over potential, not to utilize it completely in the range.
Okay, so very good question, and I appreciate your question. Okay, and so what happened? Let's say this is your electrode area, and you are giving fuel here at a pressure P, and then it is moving like this. We take flow field, it goes out like this.
Okay.
Now, if I give, let's say I am drawing a current I, and if I know I current I am drawing means how much electron per unit time, how many moles of electron per unit time, we also know from the current, right? Because current means that, so now you know how much electron you need. Now what is happening? If you give exactly that much of amount of hydrogen flow, in this region, your fuel cell will be almost having starvation, because it will be there. It is known as fuel starvation, because as you are slowly, let's say you started, I'm giving a schematic, very simple diagram. Let's say you started like this, and this is inlet, let's say, and this width you think as an your gas flow. So is it that you are going to do like this, or you will be doing like this, or like that, right? So what does it mean? It means that here you are giving some amount, and you are assuming that I'll be giving this much of amount, so much, so that at the end nothing comes out. Possible? And that is what we can calculate, that how much hydrogen is required for that. But what is being done, if you do that, then in this area there will be a starvation, because your pressure will be very less. Which pressure is that? Earlier I was telling delta P is equal to P in minus P reaction. Now your P in will start coming down, because on the way hydrogen is being used, right, consumed. As hydrogen is being consumed from your flow, So your actual pressure will also start coming down. As actual pressure is coming down, so your reactant, what will happen if you want to make delta P constant, your reactant pressure will also start coming down. And if in this region, if it is very low because you have given just exactly the same amount, then you will be having this particular portion will be performing very badly. And this is known as non-uniform performance of a fuel cell. And this is, I think, Amit is going to discuss on scale up issue, some of the things he is going to touch upon. So what happens, these are the things is not that much crucial when you are doing in a 2 by 2 centimeter or 5 by 5 small small cell. But as soon as you are going from the laboratory scale to the commercial scale, you face this type of problem that huge portion of your is not performing well. And as you know that sometimes in a group few people are not good, then they also reduce the performance. So because of this small area, the overall performance of the cell also gets affected severely. So to avoid that, always people try to give some excess 10%, 20% hydrogen or fuel, and that is known as fuel utilization efficiency. So there you will be actually trying to include this one also.
Okay, sir. Thank you. Thank you for your detailed explanation.
Okay, thank you.
Can I ask?
Sure,
Can I ask one question?
Please.
Sir, what is the present scenario of India in implementation of fuel cell? What are the present scenarios? So how much percentage we have implemented, and what is the way forward in coming years?
Okay, thank you. So it's a $1 million question, number one. Okay, and nobody knows the answer. Okay, so let me tell you one thing. Even Amit was also telling the same thing in the beginning. That said there is a chicken and egg problem. Because when we are talking about fuel cell, also we talk about hydrogen. Now, where from hydrogen is going to come? But now time has come that we should start discussing this same problem in different angle. It's no more chicken and egg problem. It is a problem where you need a bride and groom. It's a marriage problem. And we should not tell that whether chicken is first or egg is first. We have to tell if fuel cell is there, hydrogen has to be also there together and hold the hands, then the only marriage is going to happen. So now that is one of the problem, that is neither fuel cell is going to come first or neither hydrogen infrastructure is going to come first. They will be coming now parallelly, and then we'll be able to see. This is the implementation point of view. Now the second thing comes that ultimately, even if somebody asked me to buy a vehicle, even now also I think that whether I wanted to buy a vehicle and I started estimating all the things, wanted to go for electric vehicle, then I realized that for going only 200 kilometers, I'll be paying around 13 lakh rupees. And after from here I go to Pune, then I have to search for a charging station, or I have to request some of my friends that would you kindly allow me to charge. And if he's having a garden with a plug point, then only I'll be able to charge. Otherwise, I'm gone. And I can tell you one of the recent thing what happens. Somebody was telling that he has bought an electric vehicle. He went to Pune. He went to Lonavala, close to from Pune. And after going there, he wanted to come to Mumbai, but he was so afraid. He went back from Pune. He told probably my charge will get discharged completely. My battery, I'm not going there. Okay. So one of the very important thing is that for the success of this is that the infrastructure very important. Like now in case of fuel cell, there are only one refueling station in India, that is in Delhi. Now if I buy a car and if I don't have a refueling station, I will be struggling, and no, so it's not going to find anyway. So now, but other than that is very important. The first step of this penetration in the market is that the public awareness. Unfortunately, it is not in other country also we have this type of vehicle running on the road. But at least if you go Germany, you will be finding that the police people, they are using the fuel cell vehicle car for patrolling, and all the people, they see the police as well as they see the fuel cell vehicle, and they have an curiosity. They ask, they understand, sometimes they go back and they see, no, it's a reality. Now for us it's a myth, still it's not a reality for us. We do not believe that's going to come. In their country they know it's going to come. It's today or tomorrow, in 5 years, 10 years, doesn't matter, but still going to come, and you'll be having a mindset. And then the second thing, so that is very important. Now at this stage we have to actually start some of the public awareness type of thing where we can have some demo prototype. Is so unfortunate in a country like us, we have only 2 demo, And out of that, one demo is happening in a particular automobile sector vehicle, where they run it as a test vehicle. If I make a vehicle, I have my fuel cell scooter just behind me also. We cannot run this scooter because there is no norms. I have to get a registration from RTO, and there is no norms for hydrogen vehicle. And if you want to run this vehicle, then you have to run below 25 kilometers per hour. Then you don't need any registration. Probably you know that electric vehicle nowadays, those things are no, you don't require any registration if it is your speed is less than that. So my vehicle is like that. Now it will not be commercial. So there are lots of other things, policy as well as in the government level, and the government is pushing a lot, definitely. And it's going to come very soon. And the target is 2030. So in next 10 years, there will be huge change. And those people are actually jumping into it in a small research and big research. Whatever is that, they will be getting definitely benefited. But the cost point of view, we should not discuss, because it's something like this. I tell all the time, so I take lots of analogy. I love taking that one. You just see a newborn baby and then you start seeing, okay, how much cost it is going to give, okay, and then you do not feed it, okay. So you just do it with affection. That's how I do. Amit is doing. Lots of you people also will start doing. Let us do with affection. And if you have affection with your kids, kids will definitely deliver you, okay, whatever you want, okay. So that's what at this point of time we should not discuss about, because it's a baby still in India. It has to go a long way. It is not running. It's not walking even. So it's a small baby. So that's what we don't want to discuss the cost, but still there is a future. Otherwise, the other big industry, big company, they will not be jumping into it and then making the prototype and investing lots of money. So it's having future, and we should also start working on it.
Thank you, sir, for your insight. So, at least if you are not having any mission and vision statement, then it will be nothing. So that's why we have started our mission and vision statement. Suppose you give the example of Germany. Germany, that is already used, and some case studies are implemented through the buses, through H2. They are using fuel cells.
Yes, but in our country, the problem what happens, always we love buying from other people technology rather than, because we do not believe in risk. Okay, so we say, okay, we want to always, even all the industries, they want to live without risk and then safe route, because you see the other people, they are investing lots of money and they know they will be getting return. So in our country, that's not happening. So even I don't know, probably one day, all of a sudden you'll be finding they're buying the technology from somebody and then they are just putting in their car. That's also possible. Even in our country, lots of the other present IC engines vehicle, they have bought from some company and then they have started. So we don't know what is going to happen with R&D. They are not, but there is a vision, because they are trying now that by 2030, they want to see the vehicle running on the road. And I can tell you that we are trying also hard. Probably another, at least my vehicle is, I have some videos also, probably YouTube, some of my students, they have put, I think. So where we have scooter, we run in our campus. Amit has not seen that as well. But we have a plan in another 2 years time, we'll be having our vehicle running here, but we do not know exactly. So we'll be limiting our speed to 25 km per hour.
Sir, Atmanirbhar Bharat, you have developed, sir. That's great. One more thing, sir. The thing is that reliability. Reliability is a major concern. So that's why industry people want more reliable equipment or more reliable machine. So that is because cost is not important in case of the reliability. If the machine is reliable and give the production on the month as per target, then people will go that. Because if you think cost and a lot of breakdown, then nothing will be happen, sir.
Yes, you are right, but this is the problem. Sometimes we start talking always that I hope most of you understand Hindi, because the kahavat Hindi, because saste mein kuch acha de do. So it does not work like this, because if you want to have a reliable system, you have to pay for that. And our problem is that always for anything, even when I'm talking to our other, let's say supplier, they say that Indians, whenever we talk, first thing they ask how much it costs. Okay, so if they say how much, what is the reliability, then you forget about cost. You say I am ready for any cost, but I want reliable. But if you say you cost is my main concern, then you do not talk about reliability. And if somebody says that I want to have a work, okay, somebody somewhere.
Thank you, sir. Thank you. Great interactive session.
Okay. Any other question? Otherwise, almost I think Amit has to start with his next session.
No, sir. Actually, this is the end of the first day. Actually, yours is we can conduct only 3 sessions per day.
Okay. All right. Okay. Fine.
Yeah.
So all right. I hope there are no other questions. So Amit, I'll be sending you my this because I have written separately a chapter which will be having concise, having all these things, and which I have talked, so that you can share with them.
Sir, kindly share, sir. Because we have understood, but at least for reference, that will be very helpful, sir.
No, I'll share. I'll share with Amit. He will share with you.
Sir,
Excuse me. Yes.
I am Dr. S.K. Singh from MBM Engineering College, Jodhpur, Rajasthan.
Sure, sir. Go ahead.
Can you both plan a good NPTEL course on SWAM platform for fuel cell fundamentals and technology?
I think this is a good suggestion. I want to do. Let's see. Actually, I'm very much occupied, definitely, but I want to do something with Amit. We were thinking of whether we can now again, because sometimes back Amit was asking me about my book. The same thing. He knows very well.
No. So I feel that this will be very helpful for your book also. Once you plan a 8-week course in 8 chapters, it will be very good for speed up of your book also.
Yes, but I have now, as he was telling, I have enormous pressure from the project, and these are the very prestigious projects what I am trying to do, making a fuel cell car and all these things. And nobody, and you know that when we are in industry or research lab is different from a teacher here. Like I have to teach also in the class. I have to do lots of the things, and then I have to do a single, like Amit has left. So like that, we get a visitors and they leave after 4 years. So for us, it's a tough time, and that's the reason I'm not getting the time. Earlier, I was getting more time. Now, as time passes with the project, I think I'm really occupied. But I'm planning with Amit, probably will be doing, but it's not keeping as a commercial aspects in mind. I want to write the book, and probably we want to make it as open access. I don't want to go to any editor. Or any publisher. I want to keep it in online and in open domain, that this is what I have written. If you have anything, then you can always discuss with me. Okay, so that way probably it will be better. Everybody can get it free of cost.
Okay, thank you, sir.
I hope Amit, this is acceptable to you, right? We don't want to earn money out of this book.
Yeah, obviously, sir. I mean, if we can reach to the people with this fabulous technology, I think we don't have to wait for 10 more years. I think things will be in reality even in no time, actually.
No, even I feel
So,
that unfortunate part of our country is that we have lots of resources and resourceful people and intelligent people, but they don't get those resources required for fuel cell. And so somehow we have to reach out to all the people, and then we'll be getting this innovation coming out from a small corner somewhere. Okay, even we. So also I wanted to share with all of you, that I have almost state-of-art technology and lab here for fuel cell. I love to share with all the people, but Amit knows very well most of the equipments I handle myself, because I cannot also allow anybody to use it, because if it goes wrong, then I'll be also suffering from my. But if anytime if you need any support, infrastructure support, you are suffering, you can at least contact me. Then seeing how much time, because I have to spend my own time. And if I find that I can spend time, or I can advise you, you can come with your student or somebody, and I can spend some time, then so that's what you are always welcome in my lab. And if you can, something you can contribute to the country, that will be very good, because any one of you can contribute more than me also sometimes. Okay.
Thank you.
Yes, any more questions from the participants?
Okay, Amit.
Yes, yes, thank you very much, sir. It was very insightful and very energetic as well. I think participants have at least got some flavor of what actually is happening inside the cell. It's not just a black box that you can get to see. Things like if there are some moving things like mechanical equipments, then if something is moving, then it's very easy to understand. But If it is just some plates and some membrane and giving some current without knowing where it is coming from, then it becomes really difficult. Thank you for making that easy for even for me as well as for participants. And thank you everyone for attending the sessions. Please do attend all the sessions, because these are the basic things which you will hardly find in any of the literatures or books. I mean, if you can spend 5 days, you don't need to spend a month reading a book and trying to understand these things. So please do attend the sessions, and hope to see you tomorrow 9:30 a.m. Thank you so much, and thank you very much, sir, as well.
Thank you.
Thank you.
Thank you, sir.
Thank you so much. Thank you.
Thank you, sir.
Thank you, sir. Sir, how about feedback? Amit Bhosle.
Yes, we are working on the feedback form, so we will soon share with you all. Once that is done, I think it will be easy for you to give us a feedback.
So probably from tomorrow.
Yes, definitely. I think we'll be up with the form by tomorrow.
Okay, thank you, sir. And the link for tomorrow you'll be sending in the morning.
It is the same link. Okay, it is the same link that will work for all 5 days, for all 13 sessions, 14 sessions. So you don't need to get panicked. It's the same link that will work. Only thing is that to wait in the lobby. If someone will allow you, then you will be in the session.
Thank you, sir. Thank you.
Yeah, thank you so much. Thank you.